In our search for a theory of everything, the most elegant, beautiful, and exquisite equation is the Dirac equation. An equation that unites two big pillars of physics, quantum mechanics, and special theory of relativity. But remember, appearances can be sometimes deceptive. As all beautiful creations have a complex structure behind it, so is this equation that seemingly lures us to understand the most complex and difficult concepts of physics and mathematics. This is a new video series where you will be learning not only the Dirac equation but its related mathematics and physics concepts which will shape your understanding in a better way. My name is Shaunak. You're watching this video on my channel Physics for Students. Welcome to the very first video on Dirac equation. So first of all, what we are going to do is that we are going to go directly in understanding what is a Dirac equation. And in case of physics and mathematics, what we do is that we go for a definition. Now here is a definition of Dirac equation. It is being developed by Paul Dirac in 1928. It is a relativistic wave equation in its free form or including electromagnetic interactions. This equation describes particles that have spin half and massive. Dirac equation is important because it is consistent both with special relativity and quantum mechanics, which describes how objects travel close to the speed of light, and it has been repeatedly validated for the fine structure of the hydrogen spectrum in a completely rigorous way, and it has become a very important and vital area in building the standard model. Now, as you can see right on this equation, I have highlighted certain words in red. Now, why it is that we will come to that part, but before that, let us simplify this equation, and in a more simple language we can tell this. It is an equation developed by Paul Dirac, and it reconciles special relativity and quantum mechanics. It takes into account the spin of particles. This is the only equation which works perfectly with particles traveling close to the speed of light. It obeys the laws of quantum physics, and it has been tested very well, and it is considered as one of the most important equation of modern physics. Overall, if we deduct those technical words, this is overall the meaning of the Dirac equation. Now, if we again revisit our definition, there are certain things which come across. Number one, what do we mean by a relativistic wave equation? We need to look onto that. Second is that what is spin half and massive particles? This is also important. Also, this equation, this definition talks about something which is a free form. Now, what do we mean by that? We will look into it. Also, what is fine structure of the hydrogen spectrum? This is relevant to the context. And what do we mean by reconciliation of special relativity and quantum mechanics? Why there is a need? All those things we are going to look into it. So as usual, from any definition of either physics or mathematics or analysis, we start developing the thoughts and ideas, and Dirac equation is also not an exception. So we understood the basic meaning with a easier way of understanding. Along with that, we got certain points which we are ready to prepare. Now, in order to understand that, first let us look. It was basically plain English. How does it look like? Now, this is one of the original form of the Dirac equation, although Dirac equation can be written in form of different ways. So this can be written in this form, as well as in this form, as well as in this form. Now, the second and the third are more or less prevalent. I mean to say, this is very common. You can find it in any textbook. But the last equation requires a little bit of attention. And this is what is called a Feynman slash notation, or you can call it as Dirac slash notation. This is a little bit uncommon in terms of the books or text. This is uncommon, and I'm just going to tell you that if you encounter this kind of equation, you should not feel that what it is. So when we talk of Feynman slash notation, you see that the partial derivative has got a sign. So what does it mean? It means that it is a shorthand notation, and it deals particularly with QFT, or the quantum field theory. You can tell that it is a way of simplifying expressions involving certain contraction of gamma matrices and 4 vectors. We will look into that later, but you can understand that this is a kind of a shorthand of writing big equations into small. So let us take an example. If I take this kind of an equation, and if I take the upper indices of the gamma matrices around here, then we can say that this gamma matrices used in Dirac equation to describe the behavior of fermions, and it's preserved the structure of what we call Lorentz transformation. Also, this u or mu, which is in the lower indices, it also represents a kind of a 4 vector in a 4 vector or a 4 gradient in a space time. Now these things are, these are mathematical concepts which we will take slowly one by one. But from here what we can understand that this a slash actually means all those things. Now when we look into this Dirac equation, now you see this can be written as this. So the partial derivative slash actually means the gamma matrices which has got an upper indices, and this partial derivative which has got a lower indices, and it means something. We will look into that later. So we can say that this slash is actually representing this one. Now you might have a question, what is the use? Why are we using a slash notation instead of writing the full? So first of all, there is a lot of compactness. That means instead of writing a long sum over the components, what do we mean by components? I will come to that later. You can use the slash notation to keep things simple, and it is easy to handle. Also to read. There is a clarity because in quantum field theory, calculations often involve contractions between gamma matrices and 4 vectors, and if we use slash notation, it helps to indicate that these contractions are happening without cluttering the equations with summation indices. And there is a convention because it becomes a standard notation in the field, particularly in the context of calculations involving diracspinors, as we will later see, and interactions with fields, and this standardization helps physicists communicate complex ideas more efficiently. So we can understand that there is a compactness, there is a much more clarity, and there is also it is a convention. But in this first point, what I tried to tell you is that it reduces lot of labor. Instead of writing indices over indices, it actually contracts that. Then what do we mean by indices? Let me show you a very simple example, but we are not going to explain the mathematics right now because we are building up on that. So if you see this one, this Dirac equation, now what you can see is that these gamma matrices are actually 4 by 4. So 0, 1, 2, and 3, these are almost 16 components that we need to write. Again, if you take the del mu, although this is just a part of that, this partial derivative can be going on 0, 1, 2 and 3. Also, the spinor component, which we are going to learn what it is, actually has got 4 components: psi 1, psi 2, psi 3, psi 4. So instead of writing all those components, which will take more than 2-3 pages in order to expand this equation and write, it becomes cluttering, cumbersome, difficult to do those equations. We use this slash notation, and this actually helps us to write things more elegantly. So the expanded form, remember, it is quite a long one, and it is quite complicated, and we will explore on that. So from here what we understand is that Dirac equation is basically a relativistic wave equation. What we mean by relativistic wave, we will explore on that later. It is something which takes into account both the mathematics of special relativity as well as quantum mechanics. Obviously this equation takes into account spin half particles which creates matter particles like fermions, and the equation predicts the existence of antiparticles which are positrons. Now you might have a question, what was previous to that? Is that the earlier equations were not taking into account spin, or what? We will come to that part later. But this is an overall idea. What is Dirac equation? What is a Feynman slash notation? And what does it signifies and makes our life easy? Now, as we understand, these have got a lot of mathematics on it. So the next part of the video I would like to tell you. So yeah, here it is. Dirac equation ensures that the theory respects Lorentz invariance. That means it doesn't transform under Lorentz transformation, and it provides a framework to understand particles with spin half. So the mathematical prerequisites which are there, I will just show you one by one, and most of them you already know, so the learning of this video will be easier. What we do not know, we will build on that. Now when we talk of the mathematical prerequisites, I will tell both mathematics as well as physics. So first thing is that yes, you need to have a good understanding of special theory of relativity, which you already know. So in special theory, I am only highlighting the last point, that is relativistic energy momentum relation. Space-time intervals for vectors you already know. In terms of mathematical physics, you already know partial differential complex analysis, but I expect that you know more of what is called a bra and a cat notation, which is often called a Dirac notation. You also need to know quantum physics. Again, I repeat, you already know, but certain areas like vector space and matrices, parity transformation, and especially chirality is something which we will speak upon. You also need to know a lot of group theory, because the transformation of special orthogonal, SO3, SO2, SU2 and symmetries will come into account. And lastly, the most important is that you need to know what is a spinor, an overview, its relation to Dirac equation, a Weil spinor, Pauli spinor, Dirac spinor, and why we need what is the importance of spinor. So from here, what we can see is that we need actually 6 things to go through. First of all are the spinors, because Dirac equation, the psi, as we will say, is not an ordinary wave function, it is a spinor wave function. We need to know the chirality, because this is called left-handedness or right-handedness. We will come to that because we are trying to understand the spin of the electron. Symmetries, SU2, U1 and so on will become very important. We need group theory, because that is how the matrices will transform. We also need to know the spin of an electron and what we call parity transformation. So don't worry if you really don't know. This series of video which I am making from now on will be concentrating on developing your knowledge of spinors, chirality and so on. So I would be teaching you and build up your base, and from then on you can take things upward. So if you really don't know, you don't need to worry, because these things will be there in this entire, I would say, lesson of videos. Now the question is that, okay, we understand that these things are required, but do you justify? I mean to say, you might ask me a question that why you need to know, what is the reason? Anything in physics or mathematics really doesn't come out of reason. So I will tell you why you need to know and how does it justify your knowledge in Dirac equation. So why spinors? So first of all, you need to understand that Dirac equation actually takes into account what are called fermions, and these have got spin half, and they are important to understand spinors, because spinors take into account fermions. The second thing is that considering the electrons, or say for example the fermions, have got an half integer, that means a kind of a half spin, electrons, protons and quarks. This half spin is described by this mathematical object spinor, so that is why it is important. Also, you will see that Dirac spinors are 4 component objects, which you have already seen, and they also clearly describes what is called particle and anti-particles. So you need to know spinors in order to understand both particle and anti-particle, and Dirac equation does that. There is also an important thing which is called formulating interaction, because it is all related to particle interaction, for example fermions and gauge fields like electromagnetic. So there also spinors come into play. The components of spinors actually holds, or I would say encodes, the entire information of the quantum state. So orientation and spin, all these are encoded in spinors. And very importantly, spinors do transform in a totally different way under Lorentz transformation. So we need to have a equation which is Lorentz invariant, and then only it will actually match with special relativity. So spinors actually do take care of all those things. So I'm just telling this because you can understand what is the importance of spinors, because sometimes in physics and mathematics we do read or learn something without knowing the actual reason for that. Now the next thing which comes, it is what is a little bit technical. It is called chirality. Now say for example, if I want to isolate, okay, first let me tell you that what is chirality. Chirality actually allows the distinction between what we call left-handed and right-handed components of spinors. I will just show you this little bit technical, but it takes into account what we called is the behavior of fermions. So this is what is called the chirality equation looks like. Now, in order to isolate the left-handed and right-handed components of a spinor, what we use is a projection operators, and it is derived from this gamma 5. So this one is called the left-handed. That means the operator projects out that the left-handed component of the spinor which has got an eigenvalue of -1, and this is right-handed. The operator projects out the right-handed component of the spinor which has got a eigenvalue of +1. So from here what we can see, this gamma 5, this is which will act upon spinor and can project out the chiral components. So this sign -1 and +1, you might be wondering why it is. So the left-handed chirality associated with gamma 5 equals to -1, this has got an eigenvalue to spinors where the spin orientation is opposite to the direction of momentum. Remember that when we are talking of special relativity and particularly taking particles which are traveling at the speed of light, then there should be a momentum. So when the spin orientation is opposite to the direction of momentum, we have got a chirality of -1. And remember that in the standard model of particle physics, left-handed fermions are those that interact via the weak force, and this leads to parity violation in weak interactions. The right-handed one, which has got a +1, these have got correspond to spinors where the spin orientation is aligned with the direction of momentum. So very simple, -1 is opposite to the direction of momentum and +1 is in the direction of the momentum. And remember that right-handed fermions do not participate in the weak interaction in the same way as left-handed ones. So this is pretty important. This is how it happens. So we can say that in the standard model of particle physics, the weak interaction, as I told you, only affects left-handed fermions and making the chirality a critical concept for weak force phenomena. So in some way, although we are not studying here weak force phenomena, but in some way it is very important. So this is what it talks of chirality, and it is very much related to Dirac equation. And as you see that we need to understand spin, because spin is the central part of Dirac equation, spin half, etc. How do we do that? That is taken into account. Now the next thing which comes is that chirality is related to the Lorentz transformation and their description remains consistent. This is one thing very important. Also chirality, their description remains considered different frames. Also for massless fermions, chirality and helicity, we will understand what is helicity. They coincide, simplifying the analysis of particle interaction, and most importantly, as I told you, that antiparticles, which are a prediction and has been proved in Dirac equation, chirality will help us to understand the distinction between particles and antiparticles. So overall, what we can say is that understanding the distinction between left-handed and right-handed fermions, which is very important in standard model, how do they interact, it explain the behavior of particles under weak interactions. It analyzes high energy and massless limits and constructing quantum field theories and a kind of a unification model, which you can take Dirac equation as a part of a unification model which is uniting two pillars of physics. So it does. The next important thing which comes is our symmetries. This is pretty important because I will tell you first of all that this group SO3, the special orthogonal group, describes rotations in three-dimensional space. So because we are taking in rotation, we have to get a mathematics which will describe this rotation. So they transform under the spinor representation of the Lorentz groups, which describes spin half particles like electrons. Also, the unitary group describes the symmetry underlying electromagnetism and how charged particles interact with electromagnetic fields. This is important. And the Dirac equation can be generalized to include SU2 and U1. So we can say that this is the foundation of gauge field theories, where the Dirac field interactions with gauge fields, photons, like photons, W and Z bosons. So overall, what we can say is that grasping the fundamental interaction in particle physics, we need to know symmetries and group theory, understanding how spinors transform, interpreting the behavior of fermions, and extending the Dirac equation to more complex theories in quantum field theory, which are beyond the standard model. So we will learn that. Don't worry, we are going to look into symmetries and group theory in a very simple manner. So here comes the next concept, which is called parity transformation. And yes, I would say understanding parity transformation is important for learning Dirac equation and spinors. Why? Because parity transformation do play a significant role in analyzing the symmetries and physical behavior of systems which described by the Dirac equation. So these are few of the reasons. If you're wondering that what is parity transformation, we will come to that part later. But these are few of the reasons that if the original coordinate is flipping the spatial orientation of a system, that is how parity transformation takes place. It helps in determining whether the physical system or equation is symmetric, that means parity even. And studying parity helps determine physical laws remain invariant under spatial inversion. So if you invert the things spatially, you make sure that this is quite consistent. And parity transformation is fundamental because it is used to classify solutions to the Dirac equation and to understand the properties of particles and antiparticles. Now, if I take parity from transformation a little bit mathematically, then we can say this one, the parity operator P, which acts on a spinor. This is a spinor wave function, right? And this can be written as this, where this gamma 0 is one of the matrices in the Dirac equation, and this shows how the Dirac equation transforms under spatial inversion. We will explore this later, but just to show you and give you an overview. And remember, because Dirac equation itself is parity invariant, that means it doesn't change under parity transformation. We need to understand this. And parity actually flips the chirality of a spinor, and it transforms a left-handed spinor into a right-handed spinor. This is truly important. And this parity transformation helps us to determine the intrinsic parity of the quantum states, which are described by the Dirac equation. Lastly, we come to this part, which is a kind of a summary. It analyzes the symmetry properties of Dirac equation, understanding the behavior of spinors under spatial inversion, comprehending the role of chirality, grasping significance of parity violation, and classifying quantum states to understand the relationship between particles and antiparticles. Now you might have now a question that, okay, we understand all chirality, spinors, parity transformation, but how these concepts at all are related to each other? I'm going to say, how do they complement each other? Otherwise there is no use of learning, right? So in this part of the video, I will talk about the relation, but before that, you need to understand what is the spin of an electron, why it is important, because it specifically describes spin up using electrons, and that is the role of Dirac equation. It merges quantum mechanics and special relativity. So obviously spin is something which is intrinsic, a kind of a angular momentum, so that we will deal. And also the solution of the Dirac equation is a 4-component Dirac spinor. So we need to understand spin of an electron and the concept of helicity. Helicity here means the projection of spin along the direction of momentum. We saw plus and minus the gamma 5. So that is what is the helicity, and it is derived from the Dirac equation. So obviously it is quite evident that spin of an electron is very much important to this. So that is what I was telling, that now we will explore that how these concepts are related, because if they are not having any relation or relevance, then why should we go? So first we talk of the spinors. And these are mathematical objects which describe spin half, and Dirac equation solutions are 4-component spinors. So we need to know the spinors. Chirality, we have already looked into it. You see the diagram shows left-handedness and right-handedness, and it helps to distinguish between particles and antiparticles, and as because these are inherent things in Dirac equation, so that would be required. Symmetry, yes, because this describes the invariance under specific transformation. We will see what are SO3 and SU2. And Dirac equation, because it is Lorentz invariant, meaning it respects the symmetries of space-time, so we need to have an understanding of symmetry. So this is giving you an idea that why we are learning and how they are related. Group theory, very much, because it is a mathematical study of symmetries, and it defines how spinors and their components are related, so we need to know this. Parity transformation, yes, it is a symmetry operation that involves the flipping of the spatial coordinates, and parity is related to chirality in Dirac equation. And finally, we talk of electron spin, which is quite evident because it has a spin half, and Dirac equation is taking care of that. So these are how these concepts are related, why we need to study how they actually contribute in our understanding of Dirac equation. Now this is a schematic diagram which will make you understand everything in a single kind of a single diagram. So first we need to know the spinors. Why? Because spinors are the fundamental objects that describe the spin of an electrons. Then we need to go to the next step, what is chirality and parity transformation. Why? Because these describe how the spinors behave under spatial inversion, which is crucial for understanding weak interactions. Symmetry. Why? Because including Lorentz and internal symmetries ensure that the Dirac equation is consistent with the fundamental symmetries of nature. Then comes what is called the group theory. Why? Because it provides the mathematical framework to describe the symmetries and the transformation properties of spinors. And finally, the electron spin, the physical property that the Dirac equation explains, integrating the concept of spinors, chirality and symmetries into a coherent theory of relativistic quantum mechanics. So what we can tell finally is that together these concepts form the foundation for understanding the Dirac equation, which provides a complete and an accurate description of spin half particles in the context of quantum mechanics and special relativity. So this gives you a complete chain, isn't it, that how things are moving and they are going from one place to another in a very nice and elegant way. Now, as I have been talking that Dirac equation is uniting special relativity and quantum mechanics, so you can understand that there is something which is called a theory of everything. We are still striving to achieve that with string theory and others. The question is that why do we need a theory of everything, or rather I would say what is the search for a theory of everything? We are going to look that into this part of the video, and also we are going to see that how Dirac equation emerges as one of the primary, prominent and very important equation in the search of a theory of everything, coming up next into this video. So as we turn the pages of our history and go back to the cave ages, we will see that human beings started to evolve. And from the ape man till today, the Homo sapiens, you can see that the skull and the brain and the entire, I would say, structure of human body slowly evolved. As we started evolving, human beings started to mature, and we first used to worship the forces of nature, which is rainfall, cloud, lightning, and whatsoever. And slowly then what happened is that we developed the hunting instruments as we slowly matured, and we become more, I would say, aware about how things should be taken care in our livelihood. And in this due process, we understand that there are four fundamental forces of nature. And among them, the first one is the gravity, the force of attraction between objects with mass, the weakest of the four forces, and it is mediated by gravitons, which are a kind of a hypothetical particle. The second is what is called the strong force, which holds the atoms nuclei together, the strongest of the four forces, and is mediated by gluons. The third is the weak force. As the name suggests, it is responsible for radioactive decay, and weaker than the strong force but stronger than electromagnetism. It is mediated by W and Z bosons. And finally we get electromagnetism, governs the interaction between charged particles, weaker than the strong force but stronger than gravity, and it is mediated by what we call photons. So in the search of a theory of everything, what we try to do is that we try to add gravity along with strong force, weak force, and electromagnetism into one single unified theory. Now the question is that have we achieved it, or will we achieve a one single GTU, or the grand unified theory? Well, time will prove that. But in the next part of the video, we are going to see some of the significant unification theories which develop in our course of time, and among them how Dirac equation comes into play. So the first great unification was done in terms of gravity and mechanics. So this showed, Sir Isaac Newton showed that the same laws that govern the motion of objects also governs things in space. So this is actually what is known as the first great unification. The second unification comes with what is called electricity and magnetism. Now it was this gentleman, James Clerk Maxwell, around 1860s, unified electricity and magnetism into the theory of electromagnetism through Maxwell's equation, showing that electric and magnetic fields are aspects of the same phenomena. The third unification which took place was between electromagnetism and weak force, and this was done by Sheldon Glashow, Abdus Salam and Steven Weinberg, which is called the Glashow-Salam or Salam-Weinberg-Abdus Salam model. It happened in late 1960s, and the electroweak theory unified the electromagnetic forces and the weak forces into a single theoretical framework. The unification was experimentally confirmed through the discovery of the W and Z bosons around 1980s. And in our context, the next unification we can call, we won't call it as a theory of everything, was between special theory of relativity and quantum mechanics. And this was done by Dirac equation, uniting these two frontiers into one single equation. Now you might have a question that why do we suddenly take into account special theory of relativity? Well, to answer your question, I would like to tell you that the motion of bodies which were traveling less than the speed of light were very well described by Newtonian mechanics for many thousands of years. But what about the motions of bodies which are traveling close to the speed of light? I mean, a special theory of relativity actually deals with that. And also, what about those quantum world where things are pretty small, and this was being dictated by Schrodinger's equation. So we already have special, Newtonian mechanics. We already have special relativity, which includes Newtonian mechanics, a kind of a subset of that, and we need a unified framework. So in order to unite the motion of bodies which are traveling close to the speed of light, and the quantum world which I would say is still dictated by Schrodinger's beautiful equation, we need a relativistic theory of quantum physics. So you were seeing, I was telling that what do we mean by relativistic wave equation? This was this. So there were earlier attempts for a relativistic quantum mechanics, Schrodinger equation, Klein-Gordon equation, but ... I mean to say there were certain problems which we are going to explain. So you see that right now we have arrived at a situation where we understand what is the theory of everything, how the grand unification theories from Maxwell to Newton, then to Salam-Weinberg model, and then into Dirac equation. So it is a kind of a attempt for a unification. Now all these were done by this purest soul of physics, which we call Paul Adrian Maurice Dirac. And why don't we have a quick look into the life and the strange character which this person had. Who was Paul Dirac? Coming up into the next part of the video. So Paul Adrian Maurice Dirac was an English mathematical and theoretical physicist born on 8th of August 1902, who is considered to be one of the founders of quantum mechanics. Dirac laid the foundation for both quantum mechanics, quantum electrodynamics and quantum field theory. He was the Lucasian Professor of Mathematics, the chair held once by Stephen Hawking and Isaac Newton at the University of Cambridge, and a Professor of Physics at the Florida State University, and a 1933 Nobel Prize in Physics recipient. If I go a little bit into this wonderful family picture, and you can see here that this was basically the house where he lived, and if I really zoom this portion of the building just beside the window, this is at 15 Monk Road, Bishopston, Bristol, then I would get this kind of a plaque. And the plaque tells that he was a Nobel Prize laureate in 1933 who revealed so and so. Look into this family beautiful picture. This is Charles Dirac, his father. This is Paul Dirac. This was his father, Felix' brother, unfortunately committed a suicide. This was his sister, Betty, and this was her mother, Florence. Now, Florence Hannah Dirac actually was born to a Cornish Methodist family, and she was named this this name Florence Hannah Dirac after Florence Nightingale, who his father actually met Florence Nightingale on a ship which was going to the Crimean War. So this gives you a kind of a understanding of the family picture. Now this was actually the school where Dirac was educated, Bishop Road Primary School, and then he went to the all boys Merchant Ventures Technical School. Dirac studied electrical engineering on a City of Bristol University. He got a scholarship at the University of Bristol's engineering faculty. Shortly before he completed his degree in 1921, he sat for the entrance examination for St. John's College, Cambridge. He passed that with an award of £70 during that time, but this fell short for his study to go to Cambridge. And despite having graduated the first class honors of bachelor's degree in electrical engineering, the economic climate of the post-war depression, and you can understand which war I am talking about, the First World War, was that he was unable to find a work as an engineer. Instead, he took up an offer to study as a Bachelor of Arts degree in mathematics at the university, and in 1923 Dirac graduated once more and this time he received £140, which was good enough for him to study and go for a scientific research. In 1937, Dirac married Margit Wegener, a sister of the famous physicist Eugen Wegener, and a divorcee. Dirac raised Margit's two children, Judith and Gabriel, as you can see right on the picture, as if they were his own. Paul and Margit Dirac also had daughters named as Mary Elizabeth and Florence Monica. And Margit, known as Mancy, had visited once in 1934 in Princeton, New Jersey, from the native Hungary, and while at dinner at Annex restaurant, he made the lonely looking man, I mean to say, his name as Paul Dirac. So his account, I would say, was made from a Korean physicist, Y.S. Kim, and he told that it is quite fortunate for the physicist community that Mancy actually took, his wife took care of everything, and Paul Adrian Maurice Dirac published 11 papers during the period of 1939 to 46, and this was obviously made possible. Why? Because the reason that Mancy took care. So because we have a saying that behind every successful man there is a woman. So this again proves to be so. And finally, the great prize of physics, the Nobel Prize, came in 1933, and it was jointly awarded with Erwin Schrödinger, and it tells that for the discovery of a new productive forms of atomic theory. Now we will explore that, and this is something a kind of a coincidence, because on the right hand side Heisenberg, as you can see on the picture, is standing a purely classical theory of quantum physics, and on the left hand side stands Dirac with a quantum, I would say, relativistic quantum theory. We see that Paul Dirac had a strange kind of a I would say character, and this had made him even more popular. So Dirac was known among his colleagues for his precise and taciturn nature, and his colleagues called him a silent genius, and even named a unit which is called a Dirac unit, which was 1 word per hour. When Niels Bohr complained that he did not know how to finish a sentence in a scientific article he was writing, Dirac replied, "I was taught at school never to start a sentence without knowing the end of it." In an anecdote from 2009 biography, when Heisenberg and Paul Dirac were sailing to conference in Japan. Now, as you can understand, they were both in their 20s, and Heisenberg was definitely somebody who was a ladies' man, and Dirac obviously was someone who the person told as an Edwardian geek. And Dirac, on one such occasion, Heisenberg actually asked him that why do you dance with beautiful women? So Heisenberg replied, "When there are girls, it is a pleasure." And after considering this, Dirac actually answered that, but Heisenberg, how do you know that the girls are nice? So, and in one of the occasions, Margit Dirac told both George Gamow and Anton Capri in an interview that her husband, I mean to say Dirac, had said to a house visitor, allow me to present Wigner's wife, who is now my wife. So that was a kind of a different type of a character, and I would strongly suggest that if you, I am planning to buy this book, although I'm reading a soft copy, that is called Graham Farmellow's The Strangest Man. It's a wonderful biography written on the life and works of Dirac. So in 1984, Dirac died in Tallahassee, Florida, and was buried at Tallahassee's Roselawn Cemetery. Dirac's childhood home in Bishopston, Bristol is commemorated, and I have shown you the blue plaque, and there is a nearby Dirac Road which is named in recognition of his links with the city of Bristol. So now it is the time that we come to the core part of our video, that is, can we break down the Dirac equation and understand all those meanings? Now what I'm trying to tell is that we will take each and every component of the Dirac equation in this video to get an understanding, but I'm not going to explain and expand this exclusively. The reason is that that would take again a long time, and this is my target, which I'm going to do in the subsequent part of the videos. This is what is called the Dirac equation. First of all, let's look into what is this I. Very common, I mean to say, this involves everywhere in quantum mechanics. It ensures the relativistic invariance of the equation and allows the for the complex valued spinor wave function. This is just to give you an idea. Don't worry, we are taking up in the subsequent videos one by one. This you already know is the reduced Planck's constant, and this involves that it really works well at the quantum scale. This is something which we will take time to explore, and a set of 4x4 matrices which obeys Clifford algebra, and it incorporates both spin and certain aspects of special relativity, which will take time for me to explain. This del mu is called a 4 gradient, and it represents the derivative with respect to the space and time coordinates. The m is considered to be the rest mass, and c is the speed of light. And this is what is called as the famous diracspinor. This is the wave function that describes the quantum state of a particle. Now you see that this diracspinor again is divided into 4 parts, psi 1, psi 2, psi 3 and psi 4, on which the upper 2 parts actually signifies spin up and spin down, which has got a particle with positive energy. The next part, psi 3 and psi 4, actually they also denote spin up and spin down, but with a negative energy, and this is actually what suggests is the existence of positron, that is the antiparticles of electron. So you can now get an idea that which elements are of special relativity, which elements are of quantum mechanics, what it is all about. Now you might ask a question that this particular equation which we are talking about, this is equal to 0 instead of any value 1, 2 or 3. The question is why it is set to 0. The first thing that we get is that when we see that the equation is equal to 0, it is a mathematical way of saying that the wave function must satisfy this partial differential equations in order to represent what is called a physical state. Also it shows that the equation is a constraint that the wave function must obey. That means the solution to this equation gives us the possible wave function, and consequently it will help us to find the different states. Also this guarantees that the solutions which are with the psi wave function operator meaningfully states in both quantum mechanics and special relativity. So this equation also tells it is homogeneous equation. That means which is a standard wave equation, and quantum mechanics it implies that the differential operator acting on this psi yields no extra terms, ensuring the solutions represent valid quantum states. And what I mean by that is that the solution psi to this equation describe quantum state of particles like electrons, including the probability distribution, spin and whatever the other quantum properties. and the equation predicts not only particles with a given mass but also their corresponding antiparticles, which was a groundbreaking discovery. Now, taking this equation, I also do have a question sometimes go in our mind, just like the Einstein's field equation. Can we find out that in this equation, can you tell which part is quantum mechanics, which part is special relativity? If we try to dissect this equation, let us see. If we talk of this psi, definitely any sign of this psi immediately gives even an undergraduate that, okay, this is related to quantum mechanics. Fine. So we define this part to be of QM. If you see C, obviously anybody can say that it is related to STR or special theory of relativity. Now the problem arises with this del mu. Now this is something which incorporates both special theory of relativity, because it will have what we call the space-time invariance, the 4 vector, and also a part of quantum mechanics. The problem also lies with this gamma mu, because it will again include spinor, Clifford algebra, as well as special relativity. That means it includes special theory of relativity as well as quantum mechanics. So from here, what we can deduce is this. It is in no way you can really distinguish or dissect and find out, okay, this part is quantum mechanics, this part is relativity. And that is why it is a beautiful equation. It is so beautifully entangled with one another that you really cannot find out which part is what, except the C and phi or whatever bits. So you can think of the Dirac equation as a unification of QM and special relativity, and it is a framework that beautifully, I would say, weaves the thread of entangling all the aspects of special relativity and quantum mechanics. And that is why it is simple, and that is why it is so complex. So we will pause today in this part of the video, and I would like to give you a quick informal summary of what we have learned. So we have learned what is an overview of Dirac equation, what is Feynman / notation, how we are getting prepared in the mathematical prerequisites to understand spinors, chirality, symmetry, and so on. Why do we need a theory of everything, and where do the Dirac equation actually stands for a theory of unification? We have seen also that who was Paul Dirac, his strange nature, and also what is Dirac equation by breaking down each and every component. However, in the next part of the videos, things will be more detailed, and we are going to take the definition again, revisit those which I have marked as red, and then go into building up the mathematical prerequisites like the group theory, the spinors, and so on. So that's all for today's video. Thank you very much for taking time and watching my video. Do please hit on the subscribe button and click on the bell icon and click on all to get all the notification from Physics for Students. You can write to my email ID, which is this. You can subscribe to my other channel on general relativity, and if you want, you can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Physics for Students will be soon back with lot of videos and continuing with this video on Dirac equation. But until then, goodbye.